let's get started. Um, Before I get started, are there any questions? Okay, all right. So last class we talked about how, for the sake of carbonyls, right? If you have R or H, right, which are sort of ketones, aldehydes, right? You can reduce these molecules using a fairly mild, relatively reducing agent called sodium borohydride, right? And again, from a mechanistic standpoint, we can think about this as being an H minus, nucleophilically adding in, right? And then you quench it with a proton source, right? So it's sort of, you're adding hydrogen across this in the source of H minus followed by H plus, right? And so what you have, right, is sort of a primary or secondary alcohol. Right? So it's sort of good ways to sort of know how to make alcohols. We spent a lot of time early on describing all the things that we could do with alcohols. Now we have another way in which we can go about synthesizing them. We also sort of pointed out that with sort of molecules such as esters, right, that sodium borohydride is going to be much, much more difficult to sort of do this chemistry on. It's not that you can't reduce esters, right, with sodium borohydride. For the sake of this class, though, for all intents and purposes, we should believe that they don't tell, right? So what we want to use in this case is lithium aluminum hydride, right? And again, what we sort of said is that what's going to happen, right, is we're going to end up reducing all the way down, right, to the alcohol, right? So the idea is that we're going to go through an aldehyde intermediate, right? The aldehyde intermediate is more reactive than the aldehyde, so we're not going to be able to stop this reaction. And so, right, it's going to reduce all the way down, okay? You can use lithium aluminum hydride to reduce aldehydes and ketones. For the sake of this course, you cannot use sodium borohydride to reduce esters. Potential benefit of this would be, for example, if you had a molecule that had a ketone and an ester, and you only wanted to reduce the ester, you could do this, right? All right, so the other thing that we described is that if you want to stop at the aldehyde, you can use a reagent called Dibol. Usually written Dibol H, right? And this is where I was getting all screwed up last class, right? So Dibol is diacetyl aluminum hydride, okay? And one of the things that I want you to sort of notice about Dibol compared to lithium aluminum hydride, right, is the fact that the aluminum, right, is actually not saturated, right? In the case of lithium aluminum hydride, we have an aluminate, right? It's an Al4, right? And the aluminum carries that negative charge on it, right? Make sense? In the case of Dibol, the aluminum is neutral, right? And again, as we sort of pointed out, aluminum is right below boron, right? And we know that when boron has three things around it, what does it want to do? It doesn't like having three things. It would rather have four things. It would like to become that negative charge, right? So this is an interesting instance, right? Because the aluminum wants to take on electrons, right? And then by proxy of doing that, the aluminum is then going to take on a negative charge. So if we think about what the nature of this is, right? So again, in this case, it's going to get to an aldehyde, right? And so we can selectively use Dibol to stop it at this temperature. Now, just really quickly before I sort of get a little bit more into the mechanism, one thing that's really important about Dibol, it's actually a really difficult reaction sometimes to control and certainly over-reduce from time to time. Dibol reactions are often, they're one of these reactions that requires an experienced synthetic chemists, both to make sure that they don't set fire to the lab, as well as to make sure that they don't over reduce their alcohol. And so these are often run at minus 78 degrees Celsius. So you run these reactions at very, very, very low temperatures. Right? And minus 78 is a fairly typical super low temperature reaction that chemists will use, in large part because you can access it pretty easily with dry ice and acetone. So take dry ice acetone, you mix them together, you get that back. Okay? So, so what's happening here? Right? So if you guys had to imagine what would happen if you were to take, based upon everything that we know so far, if you were to take an ester, right, and you were to treat it with Dibol, what kind of molecule right now is Dibol, based upon what we just said? Right? Is it a nucleophile, electrophile? Is it a Lewis base? Is it a Bronsted base? Is it a Lewis acid? Is it Bronsted acid? How would you classify it? I guess Lewis acids, Bronsted acids are the same as sort of electrophile, nucleophile. Abraham. What's that?
Acid.
What kind of acid?
Lewis acid.
So it's a Lewis acid, right? You're not going to give up those electrons and you're going to get a carbene. But yeah, it's a Lewis acid, right? Because the aluminum is deficient in electrons. It only has 6. It wants to get to 8, right? So the Dibol can behave as a Lewis acid. All right? If that's the Lewis acid, where's our Lewis base? What are the most Lewis basic electrons, for example, in this? Abraham, you're on fire. Let's go with it.
After the alcohol resonates, the bond
So this oxygen here, right? So the carbonyl oxygen is the most Lewis basic oxygen on this, and as Abraham was saying, it's sort of there's resonance involved in it, right? So the intermediate that we can imagine of a Dibol is this intermediate there. Now, what do you notice about this intermediate? What are some of the things looking at this that you could tell about the change in the reactivity of the components of this reaction? Abraham.
It's very bulky.
It's bulky, could be bulky, but what about the electronics, the electronic level? What has happened by having these electrons donate to this aluminum? What has happened to this? What has happened to this? Yeah.
That becomes an oxonium. So
And what's the nature of that oxonium?
Well, it's unhappy because it doesn't want to have.
So it's unhappy, but that's more broad. Why? So what does it want to do?
Leave. Maybe.
Kind of. I mean, there is the resonance form, right? So I think what we're getting to here, what's that?
It wants its electrons back.
Yeah, it wants its electrons back, right? And so in essence, what's happening is you're increasing the charge. You're making that carbon more electrophilic, right? So again, you're not going to donate electrons into the oxygen, right? You're going to donate electrons into the carbon below it, right? Thus, you can put those electrons into it. Again, we can reason this, as we often do, based on this resonance form, right? We can just, why don't we go ahead and do this? We were talking about it yesterday. Why don't we do it now, right? We'll put a positive charge there, right? So there's the resonance form that sort of illustrates the reactivity of sort of carbonyls. All right, what about the aluminum? What's happening with the aluminum? By taking on the negative charge of the aluminum, what does this now more closely resemble? That I just mentioned like 3 minutes ago, 4 minutes ago.
Kind of looks like terpene oxide.
No, not terpene oxide. What were we talking about? Like electronically, what is this species mirror? Yeah.
It's a proton.
Proton?
Kind of like NaBH4.
Right, NaBH4. It's not a proton. Proton would be H+. What is it a source of? Not a proton. A proton would suggest that we're going to abstract it and put the 2- onto the aluminum. We don't want to do that, right? We want the opposite. Right, so you said it's like NaBH4. What is NaBH4 called? Sodium borohydride, right? So it's a better now hydride source. So by making the aluminate, right, The hydrogen has now become a better nucleophile, right? That aluminum hydrogen bond has become nucleophilic, right? Ergo, we can add in and we can get to that there. Okay. Now, what's the difference between this species and the species that we saw with Diebol, right? When the Diebol added in, right, the overall system was sort of charged. We had that O- that could readily kick out the OR and get back to the aldehyde. In this case, it's a little bit more complicated in this, but I think usually what I sort of show is that you still kind of have this aluminum here that wants to be stabilized, right? And so you can imagine a sequence of back bonding here, although that may make that a better leaving group. You also have this ability to chelate here, right? But the idea here is that the big picture here is that this complex, right? This, once you add in, it's different than the case of Diebol, right? You don't have that O-, you can't kick down, you can't leave ethanol or ethoxide, right? In this case, you have an intermediate. And this intermediate can break down if you warm it to higher temperatures, which is one of the reasons why Diebol is a complex reaction to run, and it's one that takes an expert synthetic organic chemist with really good set of hands to do right. It's also going to be a little bit substrate specific. Usually Diebol is better when it has some coordinating group nearby. Regardless, the point is this intermediate stays in the reaction. At minus 78, this complex is stable enough that it will stop here, right, in the solution, right? And then what you can do is work up the reaction. So you add water to this reaction. The water is going to quench any excess Diebol, right? You're going to warm up the reaction, and this complex will break down. Okay, so the workup. So basically what happens in Diebol is the Diebol works, right? The Diebol works. So then you can imagine water adding in, you can kick it out, you can break down to the aldehyde, right? The reason why Diebol works, and the reason why Diebol gets to the aldehyde, is that you never generate the aldehyde in the reaction. You generate the aldehyde upon workup. Does that make sense? So the reason why lithium aluminum hydride goes all the way is that you form Diebol in the reaction, right? It's a little weird to sort of a little counterintuitive, right? But basically, you make the aldehyde reacts. In this case, when you add the Diebol, you get to this complex. You never get to the aldehyde, right? At the beginning, right? All the Diebol can react. You get the selective reactivity with the ester, right? You get to this complex. Kept at these cold temperatures, the complex sticks around. And then, when you're ready, when you've reduced and you've got all this complex, then you treat it to an aqueous workup, warm up the reaction a little bit. Thus way, this will break down, form the aldehyde, and you'll get that selectivity. Abraham, you had your hand up.
So the only reason that Diebol doesn't leak is because it's cold?
Well, no, if you did LAH, it's not the only reason. But you need it to be cold in order for it not to leave. Lithium aluminum hydride, you run it at minus 76, is still going to eliminate. It's that this complex is stable at cold temperatures, right? It's a combination of the two. It's not just that it's cold, it's that there's a complex, and that complex is fairly stable at cold temperatures, such that you can control and never generate the aldehyde until you're ready to work it up. Yeah?
The oxygen's electrons from the ester is going to aluminum.
You can imagine the complex. It's a little bit more complex than this. I think the kinetics have been worked out with this. That it's like another molecule then kind of like stabilizes the intermediate. It's a bit more complicated. I think just think about that complex. If it helps to think about the oxygen making the aluminate, right, and having that four-member transition state, four-member. These are both not really what's going on. It's a more complex system going on.
So if we have to do the mechanism, we can just go
Yes,
straight from
I think this is a simple one. Just say, hey, this is different. I don't have the aluminate, or I don't have the O-. so it can't leave. And this is stable at low temperatures. Yeah.
So over there, you wrote involve with in negative 78 degrees Celsius. Shouldn't we write step 1, negative 78 degrees Celsius, and then step 2?
So okay, yeah. So workups are implied in virtually every reaction, so we leave them.
But if you're saying that at negative 78 degrees Celsius, it won't turn into the aldehyde, do we not need to specify?
The workup? Some professors may want you to. I never worry about the workup. Yeah. I mean, it's an important part of the reaction, but it's implied in virtually every reaction that we have. In virtually every reaction that we ever run, there's going to be a workup at the end. Yeah.
For the Bible, when do we put the water? Like, when do we add water?
At the very end. So that's what we're saying, the workup. So every reaction, right, guys? So we've been doing this for a while. Every single reaction that we have, there's always, it's the rare. Well, I shouldn't say it's the rare. Those are always great reactions, right? Where you simply run the reaction, get your product, remove the solvent, right, JC? Those are the best. But most of the time, those reactions are, you have some charge buildup or some salts or something in the reaction that you need to wash away. And so the majority of organic reactions tend to have a workup at the end. And it's so common that we just don't even specify them. So yes, you are correct that from the mechanistic standpoint, the workup at the end would be it. So if we want to follow this through, right, from the workup, if you're sort of asked to sort of understand how the aluminate breaks down, right, during the workup, just to sort of for completeness, right, that's before workup, after workup, right. No, first I didn't grab 2 markers and this one's right, so if we think about what's happening here, right, if you have water in this solution, right, the water is going to attack the aluminate, right, and that's the Lewis basic site, or Lewis acidic site, excuse me. Right, you have your sort of negative charge there, you have your positive charge there. You can imagine that at this point, for example, a proton exchange, right, where right, and then you could, what do you want to do here? Right, then you can imagine that leaving. Right, then you're at that acetal. Right, then you're at the hemiacetal, which we saw earlier. You should all be able to take that hemiacetal and break it down to the aldehyde. Okay? Yeah.
And we don't need to know this, right?
You don't need to know what? I showed you. It's not.
No, because people were asking about it and you said.
No. Okay. Let me be abundantly clear here. When you're talking about, maybe I misunderstood the question. When you're doing reactions, I thought my understanding of the question was when you're saying that you're going to carry out a reaction, I'm never going to penalize for basically saying, oh, you forgot to sort of discuss your workup, because every single workup is implied. So for example, on the exam, you're going to get maybe 30 points worth of questions, much like you did on the quiz, right, where you get these questions that are saying, what's the reactant, what's the product, what's the intermediate. So if you're asked for the reactant, or if you're given the reactant, sometimes the reactant won't say aqueous workup. If it doesn't say aqueous workup, if you give me the product that didn't do the aqueous workup, it's probably fine. But generally, it's implied, and I'm thinking about the workup because the workup is implied, so you can give me the product after the workup as well. Similarly, if you say, for example, show me the reagents, if you say workup at the end, It's fine. You don't say workup at the end. It's always implied that there's a workup at the end. When you're dealing with a mechanism and you're trying to get to the very end of the product, and you have to introduce water or something into the reaction, then that's an instance where you would need to know it. So I think that it's simple enough of a mechanism, right, where you have an aluminum. If you can get to this intermediate, this should be easy, right? This is just, it's hemiacetal type chemistry. Okay, so that should not be all that challenging. This is the important part, which is why I was emphasizing this. This is the part that describes the selectivity, right? But you should know the mechanism of this latter part as well. Okay. All right. Any additional questions? All right. Okay. So so that's sort of hydride additions to esters. I'm trying to remember, did we discuss? I think we discussed. If not, I'll just restate it. You guys should be able to figure out the mechanism of this. Basically, what we saw in other instances with esters, and I think I mentioned this already, but just to be safe, I'll state it again. If you take an ester, right? So what I was saying is, if you take an ester and you treat it with a hydride source, like lithium aluminum hydride, right? You get the double addition, right? It adds in, you break down to the aldehyde then reacts. The same thing holds true with, say, for example, a Grignard addition, right? If you run a Grignard addition, like methyl Grignard, for example, and I think you guys may have run this last semester, right? Likewise, just like the borohydride reaction, right? You're going to add in, right? You're going to add in. Grignard's going to add in. You're going to kick out the alkoxide. You're going to get to the ketone. What's more reactive, a ketone or an ester? Ketone's more reactive than an ester, so is it going to stop here? No. Right? So that's going to go much like very difficult to control. And after workup, show that, workup, we will get to, in this case, a tertiary alcohol. All right, so we'll get to that alcohol that you see there. Okay, so this is analogous to sodium borohydride. It's just in the instance that you have a carbon-based nucleophile. We'll discuss in a moment, a little bit later on today, how there's ways that there are specific nucleophiles, and I'm thinking specifically about cuprates that you can use in certain settings. But actually, that's not esters. It's completely different. Not completely different, but it's an ester derivative. But again, you guys should sort of know that if you take a ketone, or an ester, excuse me, and you treat it with a Grignard or an alkylithium, these are really the two that we've learned about, right? I suppose if you treated it with like an ethynyl nucleophile, right, same thing would happen. So all these carbon-based nucleophiles that we've seen, you're not going to be able to control, right, that addition. You're going to add in once. It's going to break down to the ketone. Given that the ketone is more reactive than the ester, you're going to react again. Okay, are we clear on that? Okay. All right, so here's another, kind of in a weird way related. This is, again, conditions that we've seen in the past, right? We've commonly seen, whether it's with alkenes, whether it's with, some of the aldehydes when we were talking about the acetal formation, right? We've sort of seen how, this is a fairly common reagents that we see and that we sort of ask is what happens when you take a functional group and you treat it to acid and water, right? And in the case of sort of esters, what's going to happen under acidic conditions is that you're going to get to carboxylic acids. So it turns out that if you have an ester, you can sort of what they call sort of hydrolyze. Sometimes it's called saponify. in part because this is chemistry often taking fatty esters and converting them to soap, fatty acids. This is commonly done, right? And so you can convert esters to acids using acid and water. And as we'll see, you can also convert acids. You can also convert esters to acids using basic conditions. You have to sort of neutralize it at the end, but as we'll see, you can do that as well. But let's just start with the mechanism of this, which I think you could probably get all reason. This is one of the things that I've suggested, and I occasionally suggest to students, is that when you're learning new reactions, one of the things that you can often do is to sort of practice mechanisms. There's certainly this sort of idea of sort of active, active-based learning, right? Which is certainly, I think, it's more efficient when you're sort of learning things by figuring out them yourselves. So sometimes when you see a reaction in the book for your first time, it's worth it to, and I will try to sort of encourage this thinking if I have in the past, right? That a lot of times you guys could probably figure out mechanisms of these processes before you see them. And so a nice exercise that some of you may want to do that'll help reinforce mechanism learning as well as in the long-term sort of, both proactive mechanism, like mechanism problem solving versus just knowing a random mechanism, is to take mechanisms that eventually you're expected to know and try and actually solve them on your own. And I think this would certainly represent one that you guys could perhaps figure out. All right, and so what would we imagine happening in this reaction? Same thing like we said before, right?
I was just gonna say the R gets protonated.
So this goes back to, I think, what Abraham was saying earlier. This is there's the direct way that I think makes it easier to see it, and there's the chemically sound way, which is what's more likely happening. Of the two lone pairs that I've sort of illustrated there, which one do you think is more Lewis basic? Or more basic, Bronson basic, I guess, in this case. Right, why?
Resonance.
Yeah, I mean, exactly, right? So if we think about the two options, and this is kind of goes back to what Abraham was saying earlier, right? Which one of these is more stable? This or this, right? This one's more stable, right? Because this one has resonance forms, this one doesn't have resonance forms. This one also helps, right, explain the reactivity of these molecules, one of those resonance forms being that sort of form that we often like to consider because it illustrates the reactivity, right, that a carbonyl will have, right? So, let's just go right to that. Right? What's going to happen here? Water. Right? Water's going to add in. Okay, now when we're looking at the product, what do we have to lose here?
Hydrogen.
We have to lose a hydrogen at some point, but bigger picture.
The OR.
Right, the OR, right? We don't have that R in the product, so at some point we're going to want to lose that OR. In what way will we facilitate? The OR isn't just going to leave as a negative charge, right? So we're under acidic environment, so we want things to, we're in that sort of state where we're looking at positive charges shuffling around.
You want it to be a leaving.
So, right, so if we want it to be a leaving group, get a proton transfer.
Then a reformation.
Now it's a good leaving group. Right? A good leaving group. The resonance form of this starts to now look an awful lot like the product, where all we have to do take away that proton, which use the water to do, right? And we get to our product, right? So there's a few steps in this reaction, but again, it's nothing inherently new. This is sort of consistent in many ways with the acetal reaction that we saw, right? So we're going through the acetal, but in this case, it's literally the exact same thing as the acetal chemistry, except that we have an additional, carbon-oxygen bond, right, involved. And what that means is that you can get an interchange between the two. You're not necessarily left with the acetal. You can get back to that carbonyl. Right, this is where you can get, yeah.
Sorry. If you want, I'm trying to see where you move the H. Is it okay to just put
Proton
water in?
transfer?
Yeah. Do you have to do a proton transfer, or can you actually just use water and show?
Well, so that's what I was saying last week, is that it's probably the water that's assisting the proton transfer, but if you had to show if you broke every single proton transfer into that, you're gonna go through a lot more.
But you don't mind if you do
No, not at all. That was my gift, not really a gift. Okay, so back to sort of a common theme, right, that we've described in chemistry involving acid and water. I've sort of shown you one reaction, that is hydrolysis of an ester, right? Given this knowledge, is there another reaction that's effectively up here on the board that would just require some tweaking of the conditions? I guess I'm asking you guys to read my mind a little bit, but what we've said in the past, right, is that this is a reaction where we have a whole bunch of water. So we're sort of pushing and driving the formation of that carboxylic acid by an aqueous acidic solution. So there's so much water in this, way more water, for example, than the product. So when we have reactions where water can push it in one direction, especially in this case, how would we do it in the reverse? Well, we would extrude water, right? So we can always do this reverse, right? And go from a carboxylic acid to an ester. And there's two ways that we can do that. And we'll discuss some more practical ways to do it. But one of the ways that you can do it, if your alcohol is precious, it's probably not a great strategy, but because there's better ways to do this. But you could at least in principle imagine a scenario where you're losing water to drive it in the reverse way, and there's reagents that we've developed that can do that. But if your alcohol is cheap, like if it's something like methanol or ethanol, and you're trying to make the methyl ester, you can just use a solution of ethanol rather than a solution of water, right? And that will drive the formation there, yeah.
And you also convert the carboxylic acid, like basically treat it with SOCl2 and make
Yeah, we're gonna get there.
Oh,
Yeah. So that's a two-step sequence. Okay. All right. So so that's formation of acid from esters, and you should also be able to know that you basically switch this with ROH, right? You can do it reverse. Given the time, I'm not going to go through it, but maybe you guys could do this on your own, because literally I would just be rehashing what I did, only under the charge situation. You can also do this basically with, under basic conditions, so sodium hydroxide and water. So you can hydrolyze acids using sodium hydroxide and water, and I urge you guys to sort of go through this mechanism on your own. Again, the big difference is going to be, instead of initiating this process by activating the carbonyl, you now just have an OH minus as your nucleophile. So it's more nucleophile driven and base driven rather than sort of acid or carbonyl activation, if that makes sense, right? And so what's going to happen when you do this, right, is you're going to get to the carboxylate, right, which following workup, acidic workup, you can protonate, okay? So obviously, if you have carboxylic acid, sodium hydroxide, you're going to end up with this. Again, you don't have to show the workup. You don't have to say it. Just showing you guys that that's what's going to happen. Okay, so another way that you can sort of, so these are two ways that you can go in this direction. Sort of mentioned how things like ethanol, methanol, if you have a cheap alcohol and you want to make the ester, you can just use acid and whatever. There's a few more neutral ways that you can take and go in the reverse.
Oh, we did that NaOH, that reverse one. That OH goes into the carbon, the carbon from the carbon, right?
Yeah.
Okay,
Yeah, so basically it's just,
because the water went into the proton on it.
so another, specifically this is a, we were talking earlier about reactions. They generally require workups because you have acid or base. This is a reaction that doesn't really require a workup, but it's requires a lot of other stuff. This is kind of dangerous. But it's sort of diazomethane. Okay, so if you take this molecule and you treat it with diazomethane, or some type of diazo, but it's most commonly thought of with diazomethane, you can get to methyl esters this way. So a common way historically, if you have a carboxylic acid and you want to make a methyl ester, a fairly clean way that's somewhat, I guess, neutral and doesn't really lead to any byproducts is through the use of sort of diazomethane. Now diazomethane, yeah,
What's the OH?
it's CH2. Okay, so it's CH2, double bond nitrogen, double bond another nitrogen, positive charge on middle nitrogen, negative charge on the other nitrogen. Okay, so this is a reagent that's kind of interesting. You have to be super careful with it. Like you need special glassware for this reagent because it can explode, and so you need to avoid little places of nucleation. So it's. Remember the first time I ran this, I had a blast shield up in front of me, and I was sweating profusely with heavy gloves on. It's a great reaction, but it's also kind of intense to run because you're sort of nervous you're going to blow up the fume hood. But it's a nice reaction as well. It involves a reagent that's a little bit different looking, and this might be one that's perhaps a little bit challenging at first, but the moment that you can sort of identify, I think, what's going on here, it's actually a pretty straightforward and quick mechanism. And this is an instance where the reactivity of that diazomethane and getting to the product is perhaps best viewed, much like carbonyls, and looking at the resonance form of carbonyls to understand the reactivity. Diazomethane is also one that I think is helpful to draw on the resonance form to see the reactivity. So can you guys think of a resonance form for diazomethane? Yeah, Fatu?
Moving the electrons from that nitrogen on the end
Right?
to the next one, and then moving that.
Right, that's not going to be enough.
Getting the carbon to be negative.
Yeah, so the resonance form of diazomethane that might be helpful to sort of see what's going on here is the one where you basically have a triple bond, nitrogen, and you have a negative charge on the carbon. Now, if you look at the product, right, we've got a methyl group, CH3. So what do you guys think the first step of this reaction now that we have this resonance form is? Latu, what do you think?
Take the electrons to that carbon, attach it to.
Yeah, so we've got to have that methyl group. It's got CH2. We want that CH2 to be a CH3, right? And so now we can do that, right? So I'm just gonna. Is that better to see than this? This is dying. Sorry. First day I don't bring two black markers and it's dying on me. So I'm going to switch over to blue, hopefully. What's that? Is it going to erase? Or is it going to mucky up the... Oh, yeah. All right. All right, so if we have CH2, we have this resonance form, right? We can basically get from the CH2 to the CH3, and through the process, what's going to happen? Right, we're going to deprotonate that. Right? From here, should be pretty obvious what happens. Right? We've got a methyl group with an incredibly good leaving group. We've got a carboxylate that's negatively charged, that's primed to attack. And so what's going to happen is, right, we're going to attack. We're going to leave nitrogen gas, right, and we're going to generate the methyl bond. Okay? Does that make sense? So this is an interesting reaction, sort of a neutral reaction, the only byproduct. So this is, so we were talking about the importance of workups previously. This is a reaction where usually, and the other thing with diazomethane is it's a gas, right? So it goes into solution, but over time, and so the way that you set it up is such that the diazomethane will basically start collecting this one quenching area. But the bottom line is your reaction, right? It's clean. So one of the really nice things about diazomethane is that you run the reaction, you get your methyl ester, then you can just basically evaporate the solvent, and you're done. So aside from the sweating and some of the setup, the actual reaction itself, where the reaction is taking place, is pretty clean. So this is an example of another way in which case you can make methyl esters, so diazo compounds.
Wait,
Yes.
what about it makes it so reactive? Is it that the carbon has a negative charge?
This?
Yeah, you said in general this reaction is very reactive.
Oh, the reagent. So things explode. Things explode when you go from, especially when you increase moles and you create gas really quickly, right? So a lot of things that explode, what's happening is
Same
here.
to N2 gas.
So the fact that nitrogen gas is a leaving group, the fact that this is also in itself a gas, and you can basically go from, I don't know what it usually breaks down to, probably methane, probably ethane and nitrogen, I'm guessing. It could do a lot of different things, but the point is that you're generating nitrogen and something else. And so you're going to two gases simultaneously, so yeah.
And it's not reversible because
Absolutely, yeah, the nitrogen, well, even if this is clearly an example where the moment that you get to that, it's, so this is a very, very fast reaction. Okay, so, all right, so these are some ways that you can make, this is one way that you can make an ester. Okay. The other way that you can sort of, as we sort of learned and sort of was alluded to earlier, right? Halogens are obviously very convenient leaving groups, and so halogens within sort of carbonyls bearing halogens are often really good as well. So molecules that, usually you don't have alkyl bromides. Usually it's an acyl chloride. So we usually call these acid chlorides, right? Because they're the chloride version of carboxylic acid. And as you might imagine, you guys have sort of learned that thionyl-chloride, for example, can take alcohols and convert them to you've learned that alcohols can be converted to chlorides using thionyl-chloride, and it turns out that the same reagent can be used to convert carboxylic acids to acid chlorides. Okay. Again, the mechanism of this reaction, because of the fact that there's the carbonyl there, it's going to be a little bit different than the alcohol reaction, but really not all that different. Again, the big difference here goes back to what we were talking about earlier in terms of when you have a carboxylic acid, you may be tempted to have the OH attack, but it's technically not the OH, right? It's not the worst thing in the world. But in reality, it's that other sort of carbonyl that attacks. And so if we envision let's just go over what we've been doing. Here's the resonance form. Right? So if we have a system like this where we add in, we lose the chloride, right? Chloride can add in. Right? There's some things that are perhaps similar to what we saw in the past, right? So same sequence, we simply had the carbonyl electrons attack. We leave behind the carbocation at the carbonyl carbon. That can then be attacked by a chloride. Then we get to this intermediate that we see here, right? And that intermediate, right, as we've seen in the past, right, you can lose SO2 gas and the sort of chloride, right? So much like what we saw in the past, right, depending on the order that you do here, right, you can imagine a mechanism wherein, flip that up there. Right, just rotate it around that bond. Right, so that OH is that OH, that chloride's there. What I'm left behind is the carbocation. So you could draw it this way. Again, as I stated a few classes ago, typically what organic chemists that have a little bit more experience, and so, for example, in your book or if you see online things from people that have a little bit more experience with organic chemistry, they generally, again, try to go directly to intermediates that have full octets. So this is fine, but what you'll often see is going directly to this, which again is the same molecule, it's just the resonance form. And so generally what you'll see is people showing the two steps at once, understand? Right? And then here we still have our chloride, right? And so you can have the chloride react. Occasionally this chemistry will be done with a tertiary amine. This goes back to what we were talking about, for example, with thionyl chloride, that you can run a thionyl chloride reaction with an alcohol in the absence of a base in some settings. And for example, our lab is using thionyl chloride a lot upstairs, and we don't use a base in our chemistry because nothing bad can happen, but certainly lots of things will react with HCl, and so you oftentimes don't like to have HCl form. So you could probably imagine that bases would be useful in this. It's important in this case that you have, as we'll sort of see, it's important that you have a big, bulky base, in large part because if that base has any nucleophilic properties at all, it may add into the acid chloride. So, okay, yeah.
So it would be fine if we use like pyridine or
So pyridine is probably not the go-to base for something like this because it's nucleophilic. You'd probably want to use like I think Koenig's base, which is like a diisopropyl ethyl. It's like an even bulkier.
triethylamine.
So Koenig's base is usually the go-to. Triethylamine is fine. Koenig's base is I think usually the one that people use. It's just a little bit bulkier. So it's just a little bit bulkier. It's a diisopropyl.
That would deprotonate.
Right, and so the base would deprotonate. You could say R3N, right? Just some amine, right, and play it safe. But usually, I don't know what the book said on this, but usually I think the standard is something like Koenig's base, but triethylamine is probably fine. But pyridine, if you said pyridine, it's not going to be the end of the world either, to be honest. But in truth, you wouldn't want to run it with something like pyridine. Okay, so these acid chlorides are actually highly reactive, and they can do a lot of things. One of the things that was brought up earlier, as you might imagine, can I erase? One of the things that was brought up earlier, for example, is you could for example, this is R1, you want to make an ester. right? You can make esters. Again, you guys can go through the mechanism with this. In this case, you probably also want a base. Again, it's probably something like, in this case, sometimes pyridine type bases can actually help in a weird way. So pyridine, you probably don't want to make acid chlorides in the presence of pyridine, but the pyridine, because the pyridine will add in, the pyridine at the same time, and certain amine pyridine-like bases, there's one called DMAP, can actually catalyze the process. So the pyridine adds in first, you lose the chloride, and then that's then the electrophile. Don't ask, it's just a catalytic way to do it. So usually there's a base here as well. I'll just say R3N. Again, you guys should be able to go through the mechanism of that, right? The alcohol will add in, proton transfer, lose the chloride, right? You can also make, amines, right? So if you have, let's just say R2NH as an example, you can make amides, right? So, so we sort of mentioned these earlier. We haven't really discussed the synthesis of them, right? So if a tertiary amine isn't going to lead to that because eventually you need to deprotonate right after it adds in, right? But as long as you have a secondary or primary amine, you can get to the secondary or primary amides. Okay, so you can make from these. You can make carbon-oxygen bonds. You can make carbon-nitrogen bonds. There's only one really left, unless you want to get to sulfur, right? Which you can make sulfur-oxygen bonds as well, but we won't discuss those. But carbon-carbon bonds, right? And we learned last semester, right, about one specific carbon-based nucleophile reagent that worked pretty well on sp2 halogens. Remember what it was? Not Grignards. Although Grignards can work out okay with these, right? Grignards can actually sometimes work out okay with acid chlorides because acid chlorides can be a little bit more reactive than esters. But there's one that I think is more textbook consistent. Yeah, the Gilman, right? So the cuprate, right? So Gilman, right? So say R2CuLi, remember the Culi, right? And so this is a cuprate-based reagent. Because it's not your typical sort of substitution reaction. It involves transition metal chemistry that the mechanisms of which might become a little bit more clear once we get to palladium catalyzed cross couplings, just so you sort of understand how these can be a little bit different. But for now, just sort of recognize that, let's call that R22, right? And in this case, you can also get to ketones. Okay, so acid chlorides can be versatile reagents. And so if you take an acid chloride, so you guys should know that if you have a carboxylic acid, you treat it with cyanochloride, you can get to the acid chloride. And then from there, you can convert it to a few different things. Okay. All right, I'm looking at the notebook. I think I'm going to show you guys maybe one more reaction. So let me just show you guys one more thing, just since we're on cuprate additions to sort of acid chlorides. So we've learned about carbonyls, we've learned about alkenes. We've learned about a few different organometallic reagents, right? We've learned about alkylithiums, we've learned about alkyl Grignards, and sort of talking about alkyl cuprates. So today we've talked about both alkyl Grignards and their reactions with esters, and we know how they'll react with aldehydes. We've also sort of discussed here how cuprates, right, can add into this sort of acid chlorides. And again, the mechanisms are a little bit different here. What we didn't really talk about too much, we sort of touched on this a little bit last class in terms of molecules that possess both alkenes and carbonyls for the case of reduction chemistry. right? So last class, I think we talked about how you could selectively reduce the alcohol, right? You could selectively reduce the alkene if you wanted to. You could reduce both if you wanted to, right? So we've talked about how, when you're doing a reduction reaction, you can add in both. Now, one of the things that we haven't really discussed too much about alkenes is, for the most part, we've treated alkenes, right, as nucleophiles. In virtually all the reactions that we've seen with alkenes last semester, right, you treat it with an acid, right, you treat it with HBr, it gets protonated, you treat it with bromide, it first reacts with bromide, right, even with some of the epoxidation chemistry that we were talking about, we're sort of talking about it reacting with MCPPA, which is itself an electrophile. So we've primarily talked about sort of alkenes behaving as nucleophiles, or bases. But what we haven't really talked about too much is alkenes that can behave as electrophiles. And it turns out that when we generally think of electronically deficient and electronically poor alkenes, and alkenes that can behave as sort of electrophiles, we often think about sort of when they're in conjugation, right, with carbonyls. And so if you guys were to think about some resonance forms of this molecule, right, we sort of learned about how thinking about the reactivity of carbonyls and sort of how the sort of resonance form where you put the cation at the carbonyl carbon can sort of illustrate the general reactivity of carbonyls. You'll notice here that once I've done that and I have an alkene right next to it, right, there's an additional resonance form, right, that we can imagine, right, which puts a carbon here. Or excuse me, puts a carbocation there. Right? This intermediate here is what we'll talk about a little bit later on. It's an enolate. But you can clearly see that when you have a carbonyl along with an alkene, and they're sort of they're connected by one bond, right? So they're sort of in conjugation with one another. There's an additional resonance form that emerges due to the sort of allylic nature of the alkene to the carbocation. And so, you might expect, for example, that you could react here. You might also expect that you could react here. And so synthetic organic chemists over the last century or so, plus, right, have come up with strategies to deal with this. And they've learned a lot. And so I just sort of want to point this out really quickly, especially since we just talked about cuprates. Without getting into too much detail on this, it turns out that when you think about where the most positive charge on this would be, it's the one closest to the carbonyl, right? Because that's pulling electrons away, that oxygen's right there. So highly charged nucleophilic reagents in general will prefer to react at that carbon. What does that mean? Alkylithiums, for example, are fairly charged in Grignards. So it turns out that if you treat this molecule with, say, for example, a Grignard, like, say, for example, methyl Grignard, you're going to get, after workup, you're going to get the addition sort of into the carbonyl carbon. It turns out that with sort of, that the molecular orbital, again, this is, not going to go into this that much, but in terms of the lower lying molecular orbital of this system, right, the lowest in energy pi star, if you will, is actually this one here. So you don't worry about why that's the case, just sort of beyond this class, right? But what that means is that molecules that aren't necessarily as charged, but that are still good nucleophiles, but that might not have such a charge that would lead to electrostatically being pulled here, will instead react here. And an example of that type of nucleophile is oftentimes things like cuprates. The metal basically makes it a bit of a softer, so-called nucleophile. It's not as dense in terms of charge. And so if you treat this with our, dimethyl cuprate, you can actually get the methyl group to attack that carbon as well. Okay? All right, so what are we doing with time? Okay, so it's 10:30. I basically discussed, I think, everything that I want to discuss about carbonyl chemistry. So I guess before I've got a thought, before I put up a problem on the board that we can go over, I wanted to open up the floor to any questions that anybody has. Yeah.
I have a question about the quiz. The one that's coming up, is it next week?
Yeah, oh yeah, good, thank you for reminding me. So there was some confusion. The quiz is indeed next week. I even got confused because somebody, I think it was Nana, was it Nana or JC? Somebody brought me like an old syllabus, and the date was like next week. And they showed it to me. I was like, whatever the syllabus says. And they said, oh, this is what the syllabus says. So I guess that's next week. But it's been confirmed. I looked at the actual syllabus. It is next week. And so basically everything that we've covered to date is going to be on it. I've given some guidelines, I believe. Specifically, I forget what I said. But I think it's going to be another, is it reactions mechanism? Maybe I'm going to throw a synthesis problem on there. What did I say in the syllabus? I don't remember. I haven't written it yet. I have to look back at the syllabus.
So it includes this chapter 17.
It's all carbonyl. So yeah, so anything that I've discussed is sort of fair game. So this is a good opportunity. I think there may be, I have to check. But check the syllabus. I've given you specifically the types of questions that you guys can anticipate to give you guys a little bit of guidance. Yeah. Say again? So everything.
It says only up to chapter 16, but let's try now.
Also says tentative.
I want to ask you something. What's the largest molecule I can attach to a green urine?
What's that?
What's the largest rather than E? I can attach Me to green urine. Can I attach ET? Can I attach the
Oh yeah. So
When can I
Grignard's,
stop?
just you can stop whenever you want. Yeah, I mean I think like tertiary Grignards are maybe a little bit more challenging, but I believe you can make them as well, right? Pretty sure Bisco made some at one point. Yeah, I'm pretty sure that you can do that as well. So I think don't worry about the Grignards. If you have the alkyl, the challenge is with a lot of those Grignards is that there can be sometimes side reactions to production, but for you guys, it's paper chemistry. So
What about the green urine with the carbon dioxide to make the carboxylic acid? Does that happen? Do we use that in our...
yeah, I guess I didn't cover that. I usually talk about that a little bit in aromatic chemistry.
Okay.
So so that's not going to be yeah.
This was going to be like the same one as before.
I have to check the syllabus. If anybody's seen the syllabus, I've literally given you guys exactly the types of questions that are going to be on there. So it's similar type of like on the previous one I said you're going to get 10 points of this and you're going to get 10 points of this, or I forget exactly how we broke it down. Sure.
Okay, so for the first part, it's name the reactants, reagents, and/or products.
Yep.
of the
So
reaction.
same thing as the first question.
And then the second one is show the mechanism of the following reactant. Oh, sorry, that was one. I'm
Yeah.
awful. Sorry.
I think
Name
I
the
wanted
reactants,
synthesis.
reagents, and products the same, and then it says show how you would complete the following.
Yeah.
synthesis.
So I want to give you guys a little bit of before nailing you guys on synthesis questions on the exam. I want to make sure we at least get some synthesis practice in. I would encourage you guys. We haven't really been discussing too much in terms of synthesis, but I would encourage you guys to make sure that you practice by the quiz. So that should be your encouragement to sort of get back thinking about synthesis, because you'll certainly get synthesis problems on the exam, and it's best that you put yourself and test one out on a quiz first. Yeah, Olga. They're probably good. Yeah. I think I took a look at them. I think they're pretty good. Are there synthesis problems on those? Yeah. So that would be perfect then. So it's the exact same type of quiz. Okay. That's probably a good, yeah, so the past quizzes, if you want to prepare, and then, maybe on Sunday or something, try to take a practice quiz. That might be, take out one, print one out, and try it out, but.
After
Okay, so here's, any more questions? So quiz coming up, you gotta know the reactions, and I'm trying to encourage you guys to do synthesis. So I guess mechanisms won't be involved in this one, so if you want to delay something, I suppose you can delay mechanisms, but those will certainly pop up on the exam, so you'll have to get back to them. So maybe, I always encourage you to continue thinking about mechanisms. You'll certainly see many of these mechanisms on the exam, so. I see another hand up, Henry. Did you have your hand up? All right, so here's a question, guys. Here's a question I really, really like. So I'd ask on an exam. Okay, so here's something I think is kind of cool. Okay, so here's a if you ever have an alkene that's one stereo. First of all, so if you wanted to make an alkene, there's another way that you could do this, right? Multi-step process. So if I were to give you this, and I were to ask you to make that, and I didn't show you this, just sort of refresh on synthesis, how would we do this? You could probably do it in about 3 steps. Yeah.
I was thinking about BR2 and H3.
Yep, so you go to the alkyne, and then what? If you had the alkyne, then what would you do? Once you have the alkyne, you can either go to cis or trans, right?
So I would add NaH3.
Right, so you'd use a sodium ammonia reduction to go this way. If you wanted to go to the reverse, you do the same first step, so you'd go back through that alkyne, and then what would you use to get cis?
H2.
Yeah, H2 and limiters. Right, so this is a nice little, there's our little synthesis prep. But this is more of an advanced sort of brain game here. Okay, so if you take this molecule and you treat it to MCPBA, followed by triphenylphosphine, that's another way that you can sort of do this. And a little bit more complex. This would perhaps represent a sort of a grand challenges type question on the exam. And the question would be, why might this be the case? How would this work? And what you have to sort of maybe recognize if you were to get a question like this on an exam, right, is when I do ask grand challenge questions, usually you're trying to piece a couple things together, right? You're trying to piece together things that you've learned in the past. So when you see MCPBA and that alkene, and you recognize that this question is asking about stereochemistry, what does that tell you about what you need to know about that first step? Right?
That's going to be an anti or a syn addition.
Yeah, so does the epoxide, what is the stereochemistry of an epoxide reaction? And it's syn, right? So it's not going to change the stereochemistry. I like to write I think I've told you guys this, when I'm doing chemistry on alkenes and I'm dealing with stereochemistry, it's helpful for me to think about the stereochemistry in the plane of the board, so I'm going to pucker it on its side. Notice I don't have one as a dash and one as a straight line, like a lot of you guys will occasionally do. That can't happen. That's the wrong geometry of the molecule. But you can just take this. All I've done is I've taken this and I've shifted it that way, right? And that way now I'm doing the chemistry in the plane of the board. What's going to happen, right, is that my R1 and my R2 are going to be on the same face. Is what that means. Okay. All right, so now I've got the epoxide. All right, so now I've got that. I know that that's it. I know that I'm doing stereochemistry. I know that I need to know stereochemistry, so it's important that the epoxide is done and is drawn with the right stereochemistry. Okay. All right, so now it's something new. Now it's maybe something that I may not have seen before. But I have to pull information right, from what I have seen, right? And so when you see triphenylphosphine, we really haven't seen triphenylphosphine really much at all, right? With the exception of what? A Wittig, right? Really the only place that we've seen this is a Wittig. So there's a hint, right? We see that we have an alkene in our product. What does a Wittig do? It's an alkene, right? And so we're getting a few pieces to this puzzle. And we have to try to start thinking about maybe how we might tie this together. Okay, so we've got a couple hints there that it seems like this is going to somehow involve a Wittig, and we've got 2 hints that this is going to have something to do with a Wittig. How do we make a Wittig? How do we make a Wittig salt? How do we make a Wittig illid? Lithium. Oh, how do we make Wittig illids? You should know this. That's how you make the Wittig illid once you're already at the salt. I'm going a step further back.
Oh.
How do you make the Wittig salt? What's that? You take an alkyl bromide and you treat it with what? Triphenylphosphine, right? So the triphenylphosphine is displacing the bromide. The alkyl bromide is a good electrophile. Triphenylphosphine displaces it. Anything up there a good electrophile? Epoxide. Right? The epoxide's a good electrophile. Right? So if triphenylphosphine were going to react with this, right, think about what would happen. Right? The triphenylphosphine is going to attack. What's going to happen? It's going to be backside attack, right? Sigma star. That's going to be backside attack, right? So this is another advantage of doing chemistry in the plane of the board. My R2 and my proton, when it attacks, the R2 is still going this way, and when it attacks, it's just going up. Proton's going down, it's just going to go up. So everything's staying in the plane of the board. The difference is the phosphine is doing backside attack, so the phosphine's coming this way, and the breakage is taking place that side. Yeah.
Does it actually matter which side you use?
No, it doesn't at the end of the day, but you gotta pick one.
It would matter though if we knew what R1 and R2 were, or not.
Sure, maybe.
Maybe.
If maybe. Okay, so when the triphenylphosphine adds in, right, now the triphenylphosphine is going to take a positive charge on it, and we're going to leave behind an oxide. Does this look familiar? Right. So the moment that that triphenylphosphine adds in, the one little maybe jump here, and maybe the most difficult jump in this, given everything that you guys have learned, the one jump in this is, hey, I saw triphenylphosphine react with an alkyl halide. I know epoxides are really good electrophiles. Let me try to take the triphenylphosphine and react it with the epoxide. All right? Now what do we do? Rotate. Why? Because we want the phosphine and the oxygen to be on the same face, right? And when we do that, right, the phosphine has gone 180 degrees from down here to up there, which means that the R2 group has gone 180 degrees from up there down there. And likewise, the hydrogen is going to go 180 degrees from up there, right, to down there, right? And so that's our new molecule after rotating around, right? We also know that what's going to happen here, which just for the sake of time, is those are going to form a bond, right, that we are going to eliminate to generate triphenylphosphine oxide. And the net result is the R1 the R1 and the R2, right, are on opposite sides. So all that I would do here is I would just flip it that way, and I'm back to that there. Okay, so this is just an example of the level of problems that may be coming down in terms of the grand challenge, because I know I've gotten a few questions of what do you mean by grand challenge? This is an example. The types of things I try to do on occasion on the exams is piece things together. And as you can sort of see, at first glance, it might be like, whoa, I haven't seen anything like this. But if you think through it, right, you should be able to sort of make your way through. So
So grand challenges are part of the
Exam.